Hello.
All right, sounds great.
All right, everybody, thank you for showing up today. And for spring break, speaking on Hendrix, and talk to us about transduction investors.
Well, thank you all so much for having me. I'm very excited to be here. I've only been in this area for about a year. Previously, I spent 10 years in Mississippi at Mississippi State University. Before that, I was at Rice University for my postdoc, and I got my degrees from Clemson University with my bachelor's in biochemistry and master's and PhD in bioengineering. So I'm going to talk to you a little bit today about my work, where I am now, and a bit of my motivation leading up to this point. So just a bit of introduction. So cardiovascular diseases are the leading cause of death. Nearly one in every three deaths is attributed to cardiovascular disease, and vascular calcification is a major contributor of that. So a lot of studies have shown that in chronic diseases, disproportionately, the impact of racial minorities, low-income families, and rural populations are more impacted by that. And these chronic diseases often cascade, leading one to another, being diabetes, hypertension, chronic kidney disease, and cardiovascular disease. So in cardiovascular disease, there are three main stages. There is vascular smooth muscle cell dysfunction, decreased mineralization inhibitors, as well as material deposition of hydroxyapatite. For those of you that are familiar with bone, you know that hydroxyapatite is the mineral phase of bone. And what we see in calcification is that these smooth muscle cells will deposit bone-like substances into your arteries. And there are two main types of calcification, intimal and medial, where intimal is more of the inner lining, where medial is caused by the medial lining of the artery. So just to go over a little bit more about those two differences. So in intimal calcification, you have those of you that may be familiar with atherosclerosis or have heard that term before. This is where you have those fatty deposits in the intimal lining of the artery from high cholesterol. But my work is focused more on medial calcification. And so we are looking at the role that the smooth muscles play, and they are all located in this medial layer of the artery. And so how they work to lead to vascular wall stiffness, high blood pressure, ventricular hypertrophy, sorry, getting tongue tied today, and peripheral arterial disease. And so, yeah, so with the main of this being the vessel stiffness, the high blood pressure, and the cardiovascular diseases. So, yes, there are treatments for vascular calcification. Most hospitals will have what they call a cath lab, the vascular lab, where they have patients coming in and out often, getting balloon angioplasty procedures, stenting procedures, bypass surgery, or atherectomy. Up top, I have an image of a stent procedure being done. So they feed a catheter with a balloon and a wire mesh around it to the site of calcification. They will then deploy that balloon, filling it with saline, and then once the balloon is taken out, you'll get a wire mesh that stays in place to reopen the artery for blood vessel flow, but then also keep that in place to maintain the structural integrity of the artery. But in the case of atherectomy, what we have here is we have a diamond blade at the end of a catheter, and it's a rotating tip that kind of goes through and cuts away all the calcification there. I heard a speech about 2 years ago from a vascular surgeon, and she was saying that we've tried to crack it, freeze it, break it, and everything, but we still aren't treating the disease itself of vascular calcification. And that's where my work focuses on, because while we do have success with these, you may have heard of someone that had a stent procedure and had to go back later to get another stent put in, or had to go back later and have a bypass graft put in, because none of these eliminate the reoccurrence of that plaque buildup. So we're wanting to treat vascular calcification at the cellular level. So we're looking at, again, going back to those vascular smooth muscle cells. And these are derivatives of the mesenchymal stem cells. However, the uniqueness of these vascular smooth muscle cells is that they are not terminally differentiated. So meaning that they come from the mesenchymal stem cells, they become a smooth muscle cell, but they then have the potential to become a different cell type. And what we think is happening, as you see in this picture here, these smooth muscle cells, depending on the substance or conditions that they're in, that they can become different cell types. And for us, we're looking more at this osteoblast-like cell type. This is what's leading to calcification or plaque in your arteries. And so this is just more looking at the smooth muscle cells and the lineage of them, showing that they come from the bone marrow and the mesenchymal stem cells. They then become a smooth muscle cell. But then you see with this, some of these have dotted lines and some have solid lines. So the ones that have dotted lines can then become some of these other cell types. And so what we think is happening is that this muscle cell then becomes a bone cell. And so we see this also with the proliferation of smooth muscle cells and that phenotype change. So natively smooth muscle cells will live in that contractile, differentiated state where they really don't proliferate much, they really don't migrate, they kind of stay where they're supposed to stay, and they work to express contractile markers and help give the arteries that elasticity that we're looking for. But when those cells become synthetic and go into that dedifferentiated state, you get increased proliferation where they travel from the media into the intima, increased migration, and then they begin to no longer express those contractile markers. So for my research, I'm focused on basically like 4 research goals. Starting with 1 being the in vitro vascular smooth muscle cell calcification model, 2 looking to inhibit Wnt signaling 3, looking at protein therapy to treat vascular calcification. And then 4, mechanotransduction of those vascular smooth muscle cells in calcification. So looking more at that vascular smooth muscle cell in vitro model. So what we've done is we have taken human aortic smooth muscle cells and cultured them in a media that has 3 millimolar of inorganic phosphate. And so we've seen that over time, from 7 and 14 days, that these cells will significantly calcify over time. And then we've also done some SEM imaging where we're able to see that these cells, not only we can see those deposits, those mineralization deposits that they make, but we can also do an analysis of this and determine that these mineralized deposits, at 7 days, we're able to detect calcium, and then at 14 days, we're able to detect calcium and phosphorus. And so again, those familiar with hydroxyapatite, you know that that is calcium phosphate. So this is the mineralized phase of bone that we're getting here. We've also done a gene array and looking at the genes that are expressed by these smooth muscle cells in their calcified state. And so for this, we looked at an osteogenic gene array. So all of these markers here are osteogenic related markers, and specifically, you may be more familiar with BMP2, RUNX2, MMP2, in terms of TGF-beta, in terms of osteoblast differentiation, but we are seeing these being expressed by our smooth muscle cells. So I'm going to talk a little bit more about a project that we are currently working on, and that was recently funded by NIH, protein therapy to treat vascular calcification. And so just a few stats to sort of illustrate the motivation for this work. So what we're looking at is that African Americans, they are affected by heart disease the most, with 22.6% of deaths compared to 18.6% with Asians, the white population being 18%, and then 12% with Hispanics. And then also, as I mentioned earlier, those persons in lower socioeconomic status are more likely to suffer from heart disease. And this is due to factors like poor access to healthcare, high stress, greater prevalence of diabetes, hypertension, and smoking. And being from the South, Southerner through and through, we have the highest rates of this, which is very unfortunate. And we also have the highest rates of chronic kidney disease. So looking at chronic kidney disease, more than 1 in 7, about 14% of US adults are estimated to have chronic kidney disease. That is about 35.5 million people. And looking at how that breaks down compared to race, gender, and ethnicity, it's more prevalent with the older population, and then also more prevalent in African Americans compared to other demographics. And then also just to talk a little bit about the stats in Ohio. So in Ohio, 1.3 million Americans have chronic kidney disease. And then we say that these numbers are probably higher because some people may not actually be aware of their condition. And then in terms of ethnicity, the rates are very similar to what we see nationwide. And then also with Ohio, looking at those southern areas of the state as well as the more rural parts of the states, we have higher rates of hypertension, diabetes, and chronic kidney disease. So what links these two? Why do these two coincide quite often? So in red, I have risk factors that are typically more cardiovascular, and then in black, we have those more kidney-specific risk factors. So with cardiovascular disease, you're going to have hypertension, diabetes, obesity, smoking, and vascular calcification. But in the kidney-specific risk factors, you will have that inflammation, oxidative stress, as well as the mineral metabolism imbalance, low serum levels of fecjoin A, and then time on dialysis. And so what is fecjoin A? Why do we bring this up? Why is it so significant? So fecjoin A is an acidic glycoprotein that is naturally synthesized in the liver. It has a high affinity for nascent apatite mineral. and it works to provide over 50% inhibitory protection for mineral precipitation in our blood serum. And so there have been studies that looked at the roles of fetuin A and how it works with how it works with the smooth muscle cells. And so that fetuin A works to inhibit chronic inflammation. And it also works to sort of chaperone those calcium mineral complexes out of the bloodstream, mostly through the kidneys. So again, I mentioned dialysis earlier and why this is such an issue for us. So with dialysis, we have patients that are experiencing kidney issues. Typically, several of these patients may already be on a transplant list. They go in for a dialysis treatment where their blood is artificially filtered through a machine, and it does the function of the kidneys, but it also works to take out some of those protective mechanisms that the body naturally produces, which is fetuin A. And so also the map that I'm showing here, this is showing the locations of these dialysis centers. And so you see obviously far more dialysis centers in the South and in the rural parts of the country, and then as well as those more urban areas. And so what we've seen with this, looking at a lot of the health disparities, is that patients from more rural areas, patients from lower socioeconomic areas will be put on dialysis earlier than other patients, and then also kept on dialysis longer than other patients. Quite often, we're seeing a lot of patients not even being offered transplants as an option for their chronic kidney disease. And so again, what dialysis does is that it strips away that fetuin A, and so they get more calcification. And so quite often these patients will actually succumb to non-kidney related complications. So quite often it will be vascular calcification, heart attack, stroke, and other issues. So what we're hypothesizing to do is to use fetuin A as a therapeutic agent. And so what we want to do is we want to monopolize those natural protective properties of that fetuin A and reintroduce it to those disease cells. Could that fetuin A work to decrease that calcification and protect the arteries from the plaque buildup? And so we have looked to characterize the binding mechanisms of that fetuin A, look at that mineral growth, and see how fetuin would work to protect calcification. So we did a little study where we looked at fetuin A and when it's combined with calcium. And so we purchased some synthetic calcium carbonate nanoparticles and put fetuin in solution with them. And so what happened is that we did XPS analysis of this, and we're looking at the elements that are present on the surface. And so in the black graph here, you can see that we are detecting oxygen, calcium, and carbon. But then when you look at the purple graph, what we're seeing when we combine these nanoparticles with fetuin in solution, that calcium is no longer detectable. We're only getting oxygen, nitrogen, and carbon peaks for that. So showing that that fetuin is working to completely shield that calcium from being detected. We've also done DLS analysis, so looking at the size distribution of these nanoparticles in solution. And so at immediate mixing of these fetuin, the fetuin with the calcium carbonate nanoparticles, we see a slight reduction in size, but over time, after 96 hours, we see a significant reduction in the size of those particles. And then also some TEM images, we're able to see the maturation of these fetuin calcium complex. So here you see the dark would be our calcium that's there, and then around it, those sort of tingly, spiky things would be the fetuin that's binding to that. This is sort of the mid stage where it's maturing, and then here you see that the fetuin has developed a clear corona completely surrounding that calcium nanoparticle. And so we also then wanted to move on and do some in vitro studies. So looking at how the veteran would work in vitro and how it would work to protect these vascular smooth muscle cells. So we did a study similar to what we had done before, where we calcified these cells for 7 days, and then we added fetulin in a normal media, fetulin in calcified media, and then we wanted to see what would happen to these cells if we calcified them for 7 days and then did nothing. Would they revert back on their own, or would they continue to calcify over time? And so what we see is that we did get some results, but not quite what we were looking for. So fetulin did work to slightly reduce calcium content in the cells, but that was only in the normal media, but not so much in the calcified media. But we did see significantly here, so this is the Western blot analysis looking at the alpha-synuclein actin, which is the contractile marker that's native for these vascular smooth muscle cells. And you see when it's calcified for 7 days, we completely lose that alpha-synuclein actin, and then we also completely fetulin A being expressed by these cells. But we did see that we're able to protect fetulin A in our fetulin treatment. So that was good to see. So then we also looked at going back to gene expression, looking at RUNX2, which is a bone marker that I spoke about earlier. And so we're seeing that we do get overexpression of RUNX2 in our calcified cells after 14 days. And we do get continued expression of that RUNX2 with the fetulin in the calcified treatment, but a little less in the normal treatment. So what we wanted to look at was, okay, so we got some good results with the fetulin treatment, but can we get even better? So we are looking at using different concentrations of fetulin with this. So we looked at 9, 12, and 15 micromolars of fetulin. And the 15 is the physiological concentration of fetulin. So what would happen when we do that? And we did get significant reduction in calcification with that high fetulin concentration. So I spoke about this work being recently funded by NIH, and we're very excited about that. But in addition to doing studies to look at how can we reestablish those native fetulin levels as a therapeutic, we're also doing a community-based project with this. And so we are working with our local community to get out and inform the community about the role that their diet plays in heart health as well as in chronic kidney disease, and how we can help them to mitigate those issues before they become so severe. So I put up this map just to kind of talk about food deserts. So anyone ever heard the term food desert? So that basically refers to an area that has low access to healthy foods. This map talks about opportunity zones. So opportunity zones are where they are not quite a food desert, but still don't have enough access to food. So this is a paper by Forbes where they have identified these opportunity zones where we can do some small interventions to help save these areas from becoming food deserts. But again, as you see, the majority of these are in the South and in the rural parts of America. And so with patients not having access to healthy foods, access to fresh foods, a lot of people will rely on processed foods, right? So like I said, I recently moved to this area from Mississippi. I was in a small town, Starkville, Mississippi. I grew up in rural South Carolina. And so even when I go back home, there's like one grocery store that's available in the town. And I've even like experienced having conversations with my family to tell me that no, Dollar General is not a grocery store, because that's what they have the most access to, right? So you can drive every corner. There's a Dollar General, but people have to drive 20 and 30 miles to get to a grocery store. And so those processed foods contain phosphate additives. And so this is typically ranging from about 300 to 1,000 milligrams of phosphorus per day. And so just looking at common processed foods that most people have in their diet: soda, processed meats, cheese, bread, and rice. Definitely looking at more ethnic communities and how much more phosphate these foods have, and then looking at the percentage of the daily value, like how much phosphate that the USDA says that we should have in our diets compared to what eating these foods would do. And so the surplus amount of phosphate significantly contributes to kidney damage, but also it significantly contributes to calcification of these vascular smooth muscle cells. So we are working with local groups of high school students to teach them about healthy practices for food, heart healthy practices in terms of like being able to mitigate getting chronic kidney disease and heart disease before it becomes an issue, and then having these students sort of be the more responsible people to teach their community about how to eat healthy. And so the students will then host health fairs for their communities to teach their family and their community about what it means to be heart healthy. So just to, before I wrap up here, talk about mechanotransduction and the role of it in vascular smooth muscle cell calcification. So mechanotransduction is when these cells will interpret and react to maximum cyclic strain by activating these different signal pathways and various methods to cause calcification. And so this is essential for optimal functioning of cardiac and vascular tissue. It responds to changes in pressure and different types of stress and strain caused by downstream alterations, mostly hypertension for these vascular smooth muscle cells. And so looking at the role that hypertension plays to induce mechanotransduction. And so it works to drive vascular remodeling, expanding the hydroxyapatite deposition in the blood vessels. It will more significantly lead to medial calcification as opposed to that intimal calcification where you get more fatty deposits, and it causes increased cyclic mechanical loads that leads to vascular smooth muscle cell dedifferentiation into those osteoblast-like cells. So our lab is looking at what are the pathways that this is affecting and how is this driving this differentiation. So up here you have your smooth muscle cells and when they are impacted by mechanical strain. These are all the different pathways that are activated. So calcium pathway, our phosphate pathway, and mechanotransduction. And so what we're focused on is this Wnt pathway here down the middle. That is sort of the bridge between phosphate and mechanotransduction. So looking more into the Wnt signaling pathway. So Wnt is a protein that works to sort of activate that pathway to then lead to the dedifferentiation of these vascular smooth muscle cells. And the way that it works is that Wnt will bind to the transmembrane receptor of Frizzle and LRP56. This then leads to a stabilization of this disheveled complex that then protects beta-catenin, and then with the overexpression of beta-catenin, that then translocates to the nucleus to cause the transcription of different target genes. When Wnt is not present, the disheveled complex is not stabilized, and so it is activating to degrade and phosphorylate that beta-catenin, which then leads to the breakdown of it, and you don't get the expression of RUNX2. And so we're looking at the role that this has and seeing if it's being activated when the cyclic strain is applied to our cultured vascular smooth muscle cells. So for this work, we are using a flex cell tension system. So the FX6000, and it works to apply a vacuum. And with that, it applies strain over the cells to then sort of mimic what we see in hypertension. And so We've been using a heart waveform with that and applying up to 23% max strain over these cells. And this is our hypertension regimen. And so then we're also doing cell culture in these and stretching these cells. We're culturing them for 72 hours and then doing stretch studies for 24, 48, and 72 hours. And so then we've been able to see that we are getting calcification of these cells that have been stretched over these different time periods. And so next for this work, what we're wanting to do is to look at these biomarkers that are being expressed by these cells while they're being stretched. And so we're looking at alpha smooth muscle actin, smooth muscle myosin heavy chain, which are the contractile markers, as well as reactive oxygen species, and beta-catenin and DKK1, which are both active in the Wnt signaling pathway. So that's work that we're still doing. And this work was funded by NSF. And so I just want to thank my groups that have worked with me over the years. These are all my groups over my 10 years at Mississippi State. They were very impactful for getting a lot of this beginning work going. And then this is my lab group at the University of Cincinnati. And so with that, I thank you, and I'll take any questions.
Does I actually have no idea. For the dialysis treatment, is one of the issues with the lack of this like vitamin A globosity or the vascular?
So ephedrine A is synthesized in the liver, but it circulates in the bloodstream. And so when the patients are on dialysis, it's stripping out that ephedrine that's in the bloodstream and keeping it from working to chaperone that calcium out of the bloodstream. So it then gets deposited into the arteries. Another issue that's happening there with the chronic kidney disease, they have a mineral imbalance. So they have excess levels of calcium and phosphorus in their bloodstream. So the ephedrine is already overworking, trying to take care of that, but then when you strip it out, it's no longer able to do it. So it's kind of a chicken versus egg, right? So does a calcification happen first or does the strain happen first? We're not sure. What we're looking at is doing both right now to see which one's more impactful. We have seen increased calcification in our stretch groups that haven't been put in the calcification media, as opposed to our static groups that just sat and didn't have any strain over that. Being able to mimic that, we're not sure. So another side project, you always have, that project that's going, but that next project that you have in mind, what we're looking at doing is developing a three-dimensional model. So developing a three-dimensional model where we can grow the smooth muscle cells as well as the endothelial cells and calcify them, but also do flow through them. And hopefully with that, we'll be able to mimic what's happening in our.
The Fetchman motivation, what would, I realize this is a long way question, but what would be realistic operations that would be provided at?
Good question. So what we've thought about, we're looking at two ways of doing this. So one, what we've thought about, like with cancer patients, when they are going through chemo, they will also get like iron infusions. So maybe with patients that are on dialysis, doing a Szechuan infusion to help them with that, and then reestablishing their levels back up to that 15 micromolar. But also, we think what's going to have the most impact will be a local delivery. Because those patients that are going through dialysis, they're typically meet twice a week for those dialysis treatments. And so what we're hoping to do is do a stent, drug-coated stent. So coating that stent in the Szechuan to then have more local.
This is kind of like a big question, I don't, but we have, so one of the things they also test is like, very for cursory search. I know that means so much. It's like vitamin A seems to be a common difference there as well. Are you concerned essentially about like that hyperlocation? Like in a lot of these communities, tons of where that could end up being like a side effect.
Good question. And didn't bring up this point. Wnt is also the Wnt pathway.
Okay, I think that was
Is also involved in cancer signaling. Yeah. So that's definitely something we're thinking about, but hopefully, we don't know. We'll see.
Dr. Hendrix. I will pass around this QR code. There's a- Pass around this. And like you want.
Nothing like that, more boss states.
Right, yeah. Where's the soda to go with that? Trapped in.
When you
Smart
sign
way
in,
of doing it. Smart way of doing it.
at least it's up there. Do it, come up and start grabbing food when you've signed in, and the rest of the time is yours. Everyone enjoy their spring break.
Yes.
You thought you know that?
Will most be spring break and in the lab?
Right. Oh. Well, it's good talk though. I always had a vague idea, but I never quite got fully into understanding.
Right,
I knew it wasn't diabetes or whatever Dr. Pope used to say.
Yeah.
I knew it wasn't.
Oh, yes. Is Madison gonna join us for lunch?
She can't, unfortunately. She works downtown, and then it can be difficult for her to get away from work.
Oh,
Get
gotcha.
down here.
Give her my love.
Right, she sends her wants to be here. She actually works with the cardio metabolics downtown there, so she was really wanting to come, and she was trying to convince her boss to give her a little time to come off, but unfortunately could not swing it.
It's a 7